Right. So moving on, I'd like to introduce you now to Sara Imran Khan. She's also a PhD student here at UNSW, and she'll be presenting her research on monitoring of algal growth metabolites under variant nutrient load using fluorescence spectroscopy.
Hi everyone. Thanks Lisa for the introduction. So this is just a brief overview of my presentation. So as we know that the synergistic effect of different environmental parameters basically leads to this cyanobacterial blooms. And these parameters are mainly the fluctuation or the availability of nutrients, light, temperature, grazing, and also turbidity and water buoyancy. So a lot of work have been done on the availability of these nutrients. As we know, these nitrogen and phosphorus, they are mainly the limiting nutrients in aquatic ecosystem, and eutrophication leads to these HABs, and particularly the cyanoHABs. It has been shown that the phytoplankton growth biomass and the species compositions are mainly influenced by the availability of these nutrients. And these shifts in the aquatic environment affects the shift of the phytoplankton as well, from diatoms to the cyanobacteria. So a lot of work have been done on these nutrients. We wanted to focus more on the nitrogen concentrations, and it has been shown that these nitrogen concentrations, they provide favorable conditions for the cyanobacterial bloom. In one study, it was shown in Lake Tahoe that a variation in nitrogen addition from as low as to 4 times, that's like around 6.2 milligram per liter, to as high as 32 times, that is 49.6 milligram per liter, it lead to an increased total proportion of microcystins. So we know that these studies, they have been showing like how these nutrients are affecting the biomass and the species composition in general, but there's still a research gap in terms of the information that is available with respect to the AOM that's been released, or the DOC that's released as these AOM, and what is the associated fluorescence signature with these nutrient conditions. In terms of the fluorescence signature, we know that these species, that is the algae and cyanobacteria, they have these pigments, they fluoresce at above 600 nanometer, and they're mainly the phycocyanin and the chlorophyll A. And these species, they also release the AOM, and these AOM are basically fluorescence in nature, and they mainly fluoresce at a wavelength below 600 nanometer. So this is like a typical excitation emission matrix of an algae or a cyanobacterial species. And these fluorescence signature, they mainly correspond to either protein-like fluorescence, or they also correspond to these traditionally derived fluorescence. Okay, so our research goal was to see that we wanted to see how these fluorescence spectra, they vary with these nutrient concentrations, and if we can find these key peak signals that could possibly help in understanding the nature of these algal metabolites released under nutrient stress conditions. So we selected basically 2 species. So there were 2 strains of Microcystis aeruginosa, CSS 555 and 564, and we selected 1 algal species. We grew these species in large 5-liter glass bottles, and they were aerated to have a uniform mixing. And we used different nutrient loads. So we just fixed the phosphorus concentrations, and we varied the nutrient load from 1 till 30 to 1 nitrogen phosphorus load. And we sampled the samples at regular interval, and they were analyzed for the cell counts, DOC, fluorescence spectroscopy, cell integrity. We also measured the molecular characterization through LC-OCD, and we measured the nitrogen and phosphorus load using ion chromatography. But I will be mainly focusing on the results based on cell counts, DOC, and the EAMS. Okay, so the samples that we gathered, we analyzed the EAMS for the filtered samples and also for the unfiltered samples. So the filtered samples, we're just mainly looking at the AOM that was released by the species, and for the unfiltered, we were looking at both the pigments and the AOM as well. So the samples that were analyzed at an extended wavelength, that is 240 to 800 nanometer, so we could capture both the pigment and fluorescence. So in terms of the analytical methods that we use for analyzing the EAMS, we use the parallel factor analysis by using Solo software. So this is basically a multivariate technique. It's used for analyzing the EAMS. It basically helps to simplify the EAMS, as we know that each EAM have like thousands of data points. So it's simply simplified and extracts the information and the underlying spectra that is available within that data set. It's a quantifiable and a qualitative technique, and we can have an estimation of the concentration as well. So if you look at this EAM, we could see that it's showing different peaks, but after perfect analysis, we could easily segregate into different components. So coming to our results, we basically saw that in general, when the nutrient load was increased, the cell biomass increased. Particularly during the first 10 days of the lag phases, for all nutrient condition, we saw that there were higher cell densities for concentration above 10:1 phosphorus. And at lower nutrient concentration, as we had expected, the cell counts was quite low, specifically for Microcystis aeruginus species. We saw that for CSS 555, there was specifically lower cell density at lower nutrient concentration, and maximum was around 10. And in terms of CS 564, it depicted better growth at higher nutrient concentration as compared to CSS 555. And for Chlorella vulgaris, it was found that it was more resistant to change in the different nutrient ratios, and it demonstrated a little difference. And it was interesting to find that it was showing a better growth at low nutrients as well. As compared to the cyanobacterial species, the cellular growth was not that significant at low nutrients. So coming to our DOC results, we found that the release of DOC was significant under nutrient stress conditions. So mainly these species, they release a lot of DOC at low nutrient concentrations. It's showing that there was basically a cell lysis. This could be that due to the fact that when there is low nutrients in the environment, there's insufficient nutrients, so these cells do not grow. There's a lack of cell division. So what happens is they lyse. They lyse and they release the intercellular organic matter into the environment. So that intercellular organic matter could be used become part of the extracellular organic matter, and it helps in further cell division. So what we observed for Microcystis aeruginus species, that there was a high amount of release of DOC at lower nutrient ratio as compared to the ambient condition. So around 10 and above, we saw that the release of DOC was lower. And also the release of DOC at higher concentration was observed at a later stage. It was not during the initial stages. So at lower concentration, we observed that the higher release of DOC was observed during the initial stages of the growth. Whereas for C. vulgaris, we observed that the DOC was comparable along different concentrations, and it was higher at higher nutrient concentrations, and it was particularly released at a later stage of growth, around stationary decline phase. In general, the variation was significant along the growth phases and was also significant among different nutrient ratios. So coming to our perfect analysis, so we collected all the data for all the nutrients along different species, and we did the perfect analysis, and we found 5-component model was validated for the analyzed data set. So there were 2 components there related more to the protein or amino acid-like fluorescence. One was tryptophan, like we call it peak T, that is like tryptophan-like fluorescence, and one peak was tyrosine-like, that's peak B. Along with that, we also observed component that had terrestrial-derived like fluorescence according to the classical nomenclature that is designated as peak C. And with that, we have 2 pigments, phycocyanin and chlorophyll A. So coming to our perfect results, we saw that there was a high release of protein-like fluorescence under nutrient stress conditions. So for Microcystis aeruginus species, we saw there's a high release of tryptophan was observed at lower nutrient ratios as compared to the ambient condition of 10:1. And and for the high concentration, we observed that the peak T was released, but it was released during the later stages of the growth. As far as for chlorella, we observed that at 1 till 10, we observed that there was a lower AM fluorescence as compared to the pigment fluorescence. Along with this, we also saw that the peak B, that is the tyrosine-like fluorescence, was observed only at the lower nutrient concentrations. It was not observed at higher nutrient concentrations. And also the peaks, the humic-like fluorescence, the terrestrial life-like fluorescence, its concentration increased with increasing the concentration of the nitrogen-phosphorus ratios. So we observed that by varying these nitrogen-phosphorus ratios, there is a change that affects how these organic matter that's released is been changing. And we also saw when we compared the LCOCD fractions, we saw that the release of DOC was mainly building blocks as compared to the biopolymers. So the study shows that when we increase the nitrogen in the ratio, the increase of low molecular organics increase in these species. And if you increase the phosphorus concentrations, the increase of high molecular weight organics increase. So it means it's an important monitoring parameter that should be given due concentration when we are looking at the cell counts and the pigment fluorescence. So AM fluorescence and its monitoring could complement the pigment fluorescence and give us a more idea about how these changes are occurring in a bloom and what is the bloom health. So for the pigment fluorescence, we saw that there was a higher release of pigments under nutrient condition. So it's a complement and saying that there's enough nutrients for the cells to grow, and that's why the pigment concentration increasing. As far as if you look at the lower concentrations, we see the pigment fluorescence is quite low. And also when we were growing the cultures, we saw that there was a marked difference in the color of the media. So the cultures that were growing and have a higher cell counts, there was green, but at lower concentrations, we saw that the color was quite pale. While for chlorella, we observed that the pigment concentration was higher at low nutrients as well. So it's indicating that there's a lower nutrient requirement for growth and pigment production for chlorella as compared to the cyanobacterial species. We did some ratios between the observed components as well. We wanted to see what's the character of AOM and how it's varying along the growth phases. So we did this a ratio between C1 to C2. C1 was the protein-like, and C2 was the humic-like fluorescence. And we saw that a higher protein character was observed for AM at the lower nutrient concentration for CSS 555. While for microcystis 564, it was observed that the protein-rich organic matter at the low nutrient concentration was observed during the early exponential phases, while at a higher concentration, we observed that it was released towards the stationary to decline phase, indicating that the species was more adaptive at higher concentration as well. And so coming to the outcomes, you could say that the nutrient ratios had a significant effect on the release AOM and pigment signals during the growth phases. And also the AOM release at low and high nutrient ratio was predominantly protein-rich in character, while the release of aromatic and organic-rich substances was evident at high nutrient concentrations. We found that chlorella was more resistant to change in nutrient ratios and depicted higher cellular growth at different nitrogen levels. And also CS555 culture at low nutrient indicated higher release of amino acids. However, the cell density observed was lowest, so indicating it was basically a stress condition resulting in the release of higher AOMSDOC. And also at lower nutrient ratio, this is 1 to 5, there was a release of tyrosine-like material for both of the cyanobacterial species that was not observed at higher nitrogen to phosphorus ratio. So it's clearly showing that these ratios are affecting how the AOM is released in the bloom, and there is I think more work should be done in looking how this AOM monitoring could be beneficial for the bloom health, for detecting the bloom health. Okay, and then I would just like to acknowledge it was an ARC linkage project, so I want to acknowledge all the partners and also Water Research Australia for the top-up scholarship. Thank you.
Do we have any questions for Sara?
Yep.
Thanks, Sara, for your presentation.
Thank you.
I would like to know the real concentration that you use in your medium, not just the proportion that you put.
So in terms of per cell basis, it would be like 6 × 10⁻⁷ milligram per liter on per cell basis.
Sorry?
So like it was like 0.6 per milligram per liter, but on per cell basis, we increased from 6 × 10⁻⁷ on per cell basis to 4.5 raised to -5 per cell basis.
I'm talking about concentration of
Yeah.
nitrogen and phosphates that you use in your culture medium.
Yeah, so we changed only the nitrogen concentration, and we added the nitrates. So the concentration of nitrate on per cell basis. So I'm talking about it on the cell basis. Like it was 6 × 10⁻, like in terms of when we preparing the media, it was 0.6 milligram per liter, and we varied up to 4.5 milligram per liter.
So you have a hypertrophic condition. So the proportion of nitrogen and phosphate, in my opinion, makes sense when you have a limited condition, okay? So for the cells, doesn't matter the proportion that you have outside if you have much more than they need. For example, it's important for the cell how much I have to uptake for my metabolites, okay?
Yeah.
So as you show us, in my opinion, there is no indication that there is some limitation of nutrients in your result. Just the proportion is different, but the amount of nutrients is so high. I don't know the cells number that you have, but seems to be so high by the color of your culture. Just a comment about this, because you put in one slide that one result that when you have I think a low relation between nitrogen and phosphate, it could indicate a limitation of nutrient. To indicate a limitation of nutrient, you need to have a very small amount of nitrogen and phosphate, because in this situation, all nutrients will be uptake inside the cell. Even when you don't have nutrient outside, cells is completely full of nutrients in some time. So just try to collaborate with your results, okay? And your best growth around 10 nitrogen for 1 phosphate with respect to the head field rate for cyanobacteria, okay? Okay, thank you.
Any other questions?
Hi, thanks. I'm not an expert in this topic, but is the outcome of your presentation, like, can you make a statement on what problem compounds cyanobacteria start producing at higher concentrations of nutrients? In other words, what kind of compounds do we see that could represent a problem at higher nutrients? I don't know if you can comment on that.
So it shows that when we increase the nitrogen concentration, or the nitrogen phosphorus ratios increases, it affects in terms, if the nitrogen concentration is increasing, low molecular organic compounds increase. And in compare, if the phosphorus concentration increases, it normally leads to the release of higher molecular organics. Yeah, and in terms of the organic matter, we observed that the protein content was, the organic matter that was released was more protein in nature at under nutrient stress conditions.
Thank you, Sara.